Recall that momentum is a vector quantity that has a sign based on direction. Do not forget that. That measures the inertia of an object, aka its resistance to a change in motion. Momentum represented by letter P is equal to mv. Applying a force over time as opposed to distance is defined as impulse, and it causes a change in the momentum of an object. For a given impulse, there's an inverse relationship between impact force and impact time. So we have impulse, force acting over time, causes a change in momentum of an object. So for a given impulse, that means if we decrease the impact force, the impact time must go up, okay? And vice versa, if we decrease the impact time, that means the impact force must go up. Example again is the age-old adage to roll with the punches. If we just let a boxer hit us in the face, we have a large impact, if we move our face with the punch, aka roll with the punch, we increase our impact time, but decrease our impact force, okay? If we lean into the punch, we're gonna have a very small impact time, but a very large force. Okay, so force and time have inverse relationship, but in both of these cases, the change in momentum is still the same, okay? Force versus time graphs. It's useful in data analysis of motion as impulse can be calculated as the area between the curve and the time axis. A positive area corresponds to momentum increasing and a negative area corresponds to momentum decreasing. So example, from 0 to 5 seconds, the area is 12 Newton seconds. So the momentum of the system has increased by 12 Newton seconds. Conservation of momentum. So remember that in the absence of external forces, momentum will be conserved in a system as a consequence of Newton's third law. The forces acting must be internal. Again, a consequence of Newton's third law. When two objects interact, they apply equal opposite forces over equal time intervals, which means a change in momentum for, say, object A is equal and opposite to the change in momentum for object B. Which when you solve gives you that the overall change in momentum in the entire system is equal to 0. So the entire system's change momentum is 0, but the objects within can exchange momentum between each other. The motion of the center of the mass remains the same. It's representative of the entire system and no external forces act. So again, even though A and B exchange momentum with each other, because there's no overall momentum exchange in the entire system, it all stays within the system. That means the center of mass system will maintain its motion before and after a collision when momentum is conserved. Your problem-solving strategy is to write down your knowns before and after the collision. You set the initial momenta equal to the final momenta, and then you solve for your unknown quantity. So again, it's the same problem-solving process as we applied for conservation of momentum, conservation of energy. As the same thing with conservation of energy, please make sure that all forces are internal and not external. So if we had friction acting between A and B right here, this would be an open system because momentum is being transferred into the ground as the objects roll along the ground. Okay, so be careful with what the problem specifies. Does it state AB system? Does it say AB ground system? Okay, if friction is acting, okay. So an AB system where friction's acting, momentum wouldn't be conserved. In an AB ground system where friction's acting, momentum would be conserved because momentum is being transferred into the ground, which is a part of the system. And that brings us to closed versus open systems. With regards to momentum and energy, a system where momentum/energy is conserved is said to be closed. No external forces act. If external forces act, momentum/energy is not conserved, an open system. So an example, a basketball earth system is open as height decreases each bounce. Energy is lost to the floor, okay? The floor is not a part of the earth, the floor is its own separate thing. But in a basketball earth floor system, it is closed as the force from the floor on the ball is internal now. The ball applies a force to the floor, the floor applies a force to the ball, so that all forces are internal, and energy and momentum is conserved because energy is given to the floor, which is now part of the system, and momentum is given to the floor, which is also now part of the system, so energy is conserved. Momentum versus time graphs. The slope of a momentum versus time graph is the net force acting on an object. Again, the idea being that force is defined as change momentum over change in time, and change momentum over change in time from this graph right here is slope. If momentum is conserved, then the sum of momentum values throughout for both objects is the same. So if we look right here at first part, the total momentum of cars prior to collision is 1 kilogram meter per second. From 3 to 5 seconds a collision occurs. We can see that because the slopes of both carts are non-zero as momentum is exchanged between the two carts. And then if we look at this green area right here, the total momentum of the carts after the collision is 1 kilogram meter per second, so momentum is conserved. Okay? Lastly, we get to inelastic collisions. In both elastic versus inelastic collisions, in both cases, momentum is conserved. Okay, people have a tendency to think that because it's an inelastic collision, momentum is not conserved. That is false. In any collision, momentum is conserved. Okay, energy is conserved in inelastic collision. An example would be 2 billiard balls bouncing off of each other. Okay, in an inelastic collision, energy is not conserved. We have 3 scenarios here. The objects bounce off of each other. But they aren't like billiard balls. It's like a car crash where it's apparent that there has been some energy lost through heat or thermal energy. Okay, you have a perfectly inelastic collision where objects stick together, or you have objects separating from each other, aka an explosion. The problem-solving strategy is that you solve for the unknown velocity using conservation of momentum, and then you compute initial and final kinetic energies of each object to determine kinetic energy loss. And that is day 4 of our AP Physics review.